There is something deeply unsettling about regularity in a universe that so rarely offers it. The cosmos, in its vast and ancient indifference, tends toward chaos, toward the slow dissolution of order, the unpredictable collapse of stars, the wandering of galaxies across billions of light years without pattern or punctuation. And yet, somewhere in the deep dark between us and the edge of what we can observe, something was repeating, not randomly, not approximately, but precisely, rhythmically, with a cadence so clean and so consistent that the astronomers who first noticed it sat quietly with the data for a long time before allowing themselves to say what they were seeing out loud. Every 16 days, without deviation, a burst of radio energy arrived at our instruments from a point in space far beyond our galaxy. Every 16 days, the universe whispered the same whisper, and then went silent again, and then whispered once more, as though it were breathing, as though something out there, ancient and unknown, had found a rhythm and intended to keep it. The story of this signal begins not with drama, but with patience, which is, more often than not, how the most important discoveries in astronomy begin. It begins with an instrument called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope unlike most people imagine when they picture one. There is no dish, no towering white structure aimed at the sky. CHIME is instead a series of enormous cylindrical reflectors laid out across a hilltop at the Dominion Radio Astrophysical Observatory in British Columbia, Canada, fixed in place and relying entirely on the rotation of the Earth to sweep the sky overhead. It does not point, it listens. It listens to an enormous swath of sky every single day, collecting data in volumes so vast that it requires sophisticated computational pipelines just to begin sorting through what it hears, distinguishing the murmur of our own planet's radio interference from the genuine signals arriving from billions of light years away. It was built primarily to map hydrogen gas across the universe, to study the large-scale structure of the cosmos by detecting the faint 21-centimeter emission line produced by neutral hydrogen atoms. But in doing so, it became one of the most powerful detectors of fast radio bursts ever constructed. And it was within this context of deep and patient listening that the signal arrived. Fast radio bursts, known among astronomers as FRBs, are among the most genuinely mysterious phenomena in modern astrophysics. They are pulses of radio energy, extraordinarily brief, lasting only milliseconds, that carry within them the energetic equivalent of what our sun releases over the course of an entire year, compressed into a flash so short that most burst completely before a human eye could blink. They arrive from cosmological distances, meaning from outside our own galaxy, from sources so far away that the light, or rather the radio waves, we detect have been traveling toward us for hundreds of millions, sometimes billions of years. And for a long time after their discovery in 2007, when astrophysicist Duncan Lorimer and his student David Narkovic first noticed one buried in archival data from the Parkes Radio Telescope in Australia, they appeared to be entirely one-time events. A burst, a single flash, then nothing. No repetition, no structure, no pattern that could be used to understand what had produced them. The universe, it seemed, was sending postcards with no return address and no message. Only the faint impression that something extraordinary had occurred. The mystery deepened as more bursts were detected over the following years. By the time CHIME came online in 2018, hundreds of fast radio bursts had been catalogued, but they all shared that same strange characteristic. They flashed once and vanished, leaving astronomers with no ability to study them before or after the event. No chance to point other telescopes at the source in time. No way to observe whatever it was that had created them. And then, in 2016, something changed everything. A team working with the Arecibo Radio Telescope in Puerto Rico reported that a particular fast radio burst, designated FRB 121102, named for the date of its first detection, November 2nd, 2012, had done something no other FRB was known to do. It had repeated. Not once, but multiple times. Bursts from the same location in the sky, arriving sporadically, unpredictably, but undeniably from the same point in space. This was FRB 121102A, later confirmed through radio interferometry to originate from a dwarf galaxy approximately 3 billion light-years from Earth. And its discovery shattered the assumption that all fast radio bursts were catastrophic, one-time events. If this one could repeat, it meant the source had survived whatever process was generating these bursts, and it meant that astronomers now had something they could study over time. They could wait for it. They could listen for it. They could begin, slowly and carefully, to understand it. But even FRB 121102A, for all the revelation it offered, still didn't hand astronomers a pattern. Its repetitions were sporadic, clustered in time, appearing in bursts of activity and then going quiet for weeks or months before returning. There was no rhythm. There was no clock. Scientists were grateful for the repetition, but still unable to predict when the next burst would come or what the underlying mechanism might be. And so the field moved forward in its characteristic way, with more data, more instruments, more patience, more questions piling quietly on top of one another, waiting for an answer that seemed always just out of reach. It was within this atmosphere of accumulating mystery that CHIME, with its wide sky coverage and its relentless daily listening, began doing what it does best: finding things that other telescopes, for reasons of geography or design or timing, had simply not been positioned to find. The signal that would eventually become one of the most discussed and debated observations in contemporary astrophysics was first noticed in CHIME data collected in 2018 and 2019. The source was designated FRB 180916.J0158+65, a string of characters that contains within it, encoded in the clinical language of astronomical nomenclature, the date of first detection and the coordinates on the sky from which the signal appeared to originate. Its location, when finally pinpointed through follow-up observations using the European VLBI network, a continent-spanning array of radio telescopes working together as one enormous instrument, turned out to be a spiral galaxy approximately 500 million light-years away. A galaxy that, unlike the dwarf galaxy hosting FRB 121102a, was a relatively ordinary-looking spiral, not particularly unusual in its morphology, not particularly extreme in its star formation rate or its apparent energy output. It was, in other words, a galaxy that looked like many galaxies, and yet from somewhere within it, something was producing these extraordinary bursts of radio energy. What made FRB 180916.J0158 plus 65 different from everything that had come before? What made it the subject of a paper published in the journal Nature in February 2020 by the CHIME/FRB collaboration was not simply that it repeated, but that it repeated in a pattern, a cycle, a rhythm so precise and so consistent that when the team plotted the detections against time, they saw something that stopped them in their tracks and required them to look again, and then to check their analysis pipelines for errors, and then to check them once more, because what they were seeing seemed almost too structured to be natural. Over the course of 409 days of monitoring, from September 16th, 2018 through October 30th, 2019, the source was active, producing detectable bursts for approximately 4 days at a time, and then silent for approximately 12 days, and then active again for approximately 4 days, and then silent again for approximately 12 days, cycling through this pattern with a period of roughly 16.35 days, repeating over and over with a regularity that no known astrophysical source had ever demonstrated so cleanly before. The universe, in this corner of a spiral galaxy 500 million light-years away, was keeping time. The immediate question, the one that rose to the surface before any other, was deceptively simple to ask and extraordinarily difficult to answer. What could possibly produce such a pattern? What physical mechanism, operating at cosmological distances, would cause a source of enormous radio energy to switch on and off on a schedule as precise as a clock? The scientific community did not lack for hypotheses. In the weeks and months following the publication of the CHIME paper, theoretical proposals appeared with remarkable speed, each one offering a different explanation for the 16-day period, each one drawing on different aspects of known astrophysics, each one representing a genuine attempt to fit this strange and beautiful observation into the framework of what we understand about how the universe works. But before exploring those theories, before descending into the elegant and competing architectures of hypothesis that this signal inspired, it is worth sitting with the observation itself for a moment longer, because there is something in its simplicity, in the clean geometry of its pattern, that deserves to be appreciated on its own terms, without the rush toward explanation that so often characterizes our response to the unknown. 500 million light-years is a distance that resists genuine comprehension, even for those who spend their lives working with such numbers. The light, or in this case, the radio waves, that CHIME detected in 2018 and 2019 had been traveling through the expanding universe since a time when the first multicellular life on Earth was still hundreds of millions of years in the future, when the continents of our planet were arranged in configurations that no human eye has ever seen, when the very oceans that now cover most of our world were chemically different from what they are today. Whatever was producing this signal had been doing so, or at least the bursts that eventually reached us had been emitted, at a time when our solar system existed but bore no resemblance to what it would eventually become. And the pattern, this 16-day rhythm, had survived that journey perfectly intact, stretched and shifted by the expansion of the universe itself, but otherwise unchanged, arriving at our hilltop in British Columbia as clean and as regular as the day it was sent. Like a message from an unimaginable distance, written in the only language the cosmos speaks fluently, the language of physics. To understand why the 16-day period was so scientifically significant, and why it generated such intense theoretical activity so quickly, it helps to understand something about the landscape of astrophysical periodicity, about the kinds of rhythms and cycles that the universe does and does not produce naturally, and about what it means when something in deep space keeps time with such precision. The cosmos is not, as a general rule, a clockmaker. It produces cycles, yes, the rotation of planets, the orbits of binary stars, the pulsations of certain variable stars, the steady beat of pulsars spinning dozens or hundreds of times per second. But these cycles are the product of mechanics, of angular momentum conserved across billions of years, of gravitational forces balanced in configurations that can be extraordinarily stable. What the cosmos does not typically produce, at least not in any source previously known, is a radio burst pattern with a period of weeks. Not milliseconds, not seconds, not hours, not years, but weeks. And certainly not one arriving from hundreds of millions of light years away, where the distances involved mean that any periodicity we observe must reflect something genuinely physical and structural about the source itself, not some artifact of our own position or instrumentation. The 16-day period of FRB 180916.J0158 plus 65 fell into a range that was, by the standards of known astrophysical phenomena, deeply strange. It was too long to be explained by the rotation of any known compact object. A neutron star spinning fast enough to produce radio bursts would complete its rotation in fractions of a second, not in days. And even the slowest known pulsars have rotation periods measured in seconds, not weeks. It was too short to be easily explained by the orbital period of most wide binary systems, and yet not implausibly long either, sitting in a middle zone where several different physical systems could, at least in principle, produce the observed cycle. This ambiguity, this quality of the number 16 sitting at the uncomfortable intersection of multiple possible explanations without clearly belonging to any one of them, was precisely what made it so fascinating and so maddening to the theorists who began working on it almost immediately after the CHIME paper appeared. The first major category of explanation that researchers reached for was the concept of orbital modulation. The idea that the 16-day period reflected not something intrinsic to the burst source itself, but rather the geometry of a binary system in which the source was embedded. In this family of models, the FRB source, whatever it was, orbited a companion object with a period of 16 days, and the pattern of activity in silence reflected the changing geometry of this orbit as seen from Earth. During certain phases of the orbit, the conditions necessary to produce detectable bursts would be met. Perhaps the source was oriented favorably toward us, or perhaps it was passing through a region of denser material surrounding its companion, which could interact with the burst mechanism in a way that triggered emission. During other phases, the geometry would be unfavorable. Perhaps the companion itself would be blocking some fraction of the radio emission, or perhaps the source would be moving through a region where the surrounding environment absorbed or scattered the bursts before they could reach us. The elegance of this model lay in its simplicity. Binary systems are extremely common in the universe, and orbital periods of 16 days are entirely plausible for a range of stellar configurations.
One particularly detailed version of this orbital hypothesis was proposed in early 2020, shortly after the CHIME paper was published, by a team that included researchers from institutions across Canada and the United States. Their model centered on the idea of a neutron star, specifically a magnetar, which is a particular type of neutron star with an extraordinarily powerful magnetic field, orbiting a massive companion star, possibly a B-type star, which is a class of rapidly rotating massive star known to eject material from its equatorial regions into a surrounding disk of gas and plasma. In this scenario, the magnetar would produce fast radio bursts as a result of processes associated with its intense magnetic field, and the 16-day period would arise from the orbital motion of the magnetar around the B star. As the magnetar moved through different parts of its orbit, it would alternately pass through regions of the B star's disk, where the surrounding material could interact with the burst mechanism and enhance or suppress emission, and regions of relatively clean space, where bursts could propagate freely toward us. This model had a pleasing physical coherence to it, drawing on well-understood properties of B stars and on existing theoretical frameworks for magnetar emission, and it made specific predictions that could in principle be tested with further observations. But the orbital modulation hypothesis, for all its appeal, was not without difficulties, and other researchers were quick to point them out. One of the primary challenges was the question of what, precisely, the mechanism would be by which the orbital geometry modulated the bursts. If it was absorption or scattering by the B star's disk, then one would expect to see systematic changes in the dispersion measure of the bursts, a quantity that reflects how much free electron content the radio waves have passed through on their journey from the source to the detector, as the magnetar moved through different parts of the disk. Careful analysis of the CHIME data showed some hints of variability in the dispersion measure, but not the clear, systematic pattern that the disk absorption model would predict most naturally. If the modulation was instead geometric, if the bursts were only produced in certain directions due to the geometry of the emission mechanism, and the orbital motion swept that beam in and out of alignment with Earth, then one was essentially invoking a lighthouse model, not unlike that used to explain ordinary pulsars, but on a timescale 16 orders of magnitude longer than any known pulsar period, which required the emission beam to be extraordinarily narrow and the orbital geometry to be extremely precise. Each version of the orbital hypothesis brought with it a specific set of predictions and a specific set of tensions with the data, and no single version was clearly superior to the others in the months immediately following the discovery. The second major category of explanation was in some ways even more intriguing, because it placed the period not in the orbit of a binary system, but in something intrinsic to the burst source itself, specifically in the precession of a neutron star. Precession is a phenomenon familiar from everyday physics. a spinning top that is tilted slightly from its axis of rotation will wobble, tracing a slow cone in space as it spins, the direction of its rotational axis gradually sweeping around in a circle. Neutron stars can precess in analogous ways, and for certain configurations of their internal structure and their external magnetic field geometry, this precession could modulate the direction of any radio emission they produce, sweeping a beam of radio energy around the sky on a timescale determined by the precession period. If the precession period of the neutron star producing FRB 180.916.J0158 plus 65 was approximately 16 days, then Earth would find itself in the path of the beam for roughly 4 days out of every 16, precisely the pattern that CHIME had observed. This precession model had a different set of strengths and weaknesses compared to the orbital hypothesis. Its primary strength was that it was self-contained. It required only a single object, the neutron star, without the additional complexity of a binary companion, and it drew on physical processes that are reasonably well understood in other contexts. Neutron star precession had been invoked to explain various observed behaviors of pulsars and magnetars in our own galaxy, and the physics, while complex, was grounded in established theory. Its primary weakness was that the precession periods inferred for neutron stars in our galaxy tend to be much shorter than 16 days, typically on the order of hours to days for the most extreme cases. And producing a 16-day precession period required fine-tuning of the neutron star's internal properties in ways that were theoretically possible, but not obviously natural. Furthermore, the precession model made slightly different predictions from the orbital model about how the burst properties, the duration of the active window, the structure of individual bursts, the polarization of the radio emission, should vary over the course of the 16-day cycle. And distinguishing between these predictions observationally required more data than was available at the time of the initial discovery. What both of these models shared, however, what united virtually every serious theoretical proposal that emerged in the months following the CHIME paper, was the assumption that the source of FRB 180916.J0158 plus 65 was a neutron star of some kind, most likely a magnetar. This assumption was not arbitrary or unfounded. Magnetars had already emerged by 2020 as the leading theoretical candidate for the sources of at least some fast radio bursts. And this candidacy had received powerful observational support from a remarkable detection made in April 2020, just months after the 16-day period was announced. In that month, a magnetar within our own Milky Way galaxy, designated SGR 1935 plus 2154, produced a burst of radio energy that, while far less powerful than the cosmological FRBs detected by CHIME, was structured and energetic in a way that looked unmistakably like a scaled-down version of a fast radio burst. This detection, reported simultaneously by the Canadian CHIME telescope and by a smaller instrument called STARE-2, operating in the United States, was the first time a fast radio burst, or something closely resembling one, had been observed from a known magnetar within our own galaxy. And it provided the most direct evidence yet that magnetars could, at least in principle,
be responsible for the FRBs arriving from billions of light years away? The confirmation that magnetars were viable FRB progenitors did not, of course, resolve the question of why FRB 180916.J0158 plus 65 was repeating on a 16-day cycle. The galactic magnetar SGR 1935 plus 2154 showed no such regularity, but it did sharpen the focus of theoretical work by establishing a more concrete physical framework within which the orbital and precession models could be developed and refined. A magnetar in a binary system with a B-E star companion became, for a time, the most widely discussed scenario, partly because BE/X-ray binary systems are known to exist in our galaxy and have been studied in considerable detail, and partly because the physical interactions between a magnetar and the disk of a BE star companion offered a rich enough set of possible mechanisms that the details of the burst modulation could be explained in multiple different ways. A theoretical flexibility that, depending on one's perspective, was either a strength or a weakness of the model. As the months passed and more data accumulated, the picture grew simultaneously clearer and more complicated, as is so often the case in science. Each new observation answering one question while opening 2 or 3 others. The mystery not dissolving, but deepening in resolution. The unknown becoming not smaller, but more precisely shaped, like a fog that thins without ever quite lifting, revealing the outlines of something whose full form remains just beyond the reach of what we can see. And somewhere in that spiral galaxy, 500 million light years away, whatever was producing this signal continued its patient rhythm, indifferent to the attention it had attracted, sending its 16-day message outward into the universe without knowledge of or concern for the small blue world where a handful of curious minds were listening very carefully and trying, with everything available to them, to understand what they were hearing. There is a particular kind of scientific patience that is required when studying something you cannot visit, cannot touch, cannot manipulate, and cannot observe in any way except by waiting for it to send you information across distances so vast that the information itself ages beyond recognition by the time it arrives. Astronomy is, at its core, a discipline of patience, of sitting with incomplete knowledge and resisting the temptation to conclude more than the data actually supports, of holding hypotheses loosely enough that new observations can reshape them without shattering the entire framework of understanding that has been painstakingly constructed. The study of FRB 180916.J0158 plus 65 demanded this patience in extraordinary measure, because the signal, for all its tantalizing regularity, did not give up its secrets easily or quickly.
Each new observation added a piece to the puzzle, but the puzzle itself seemed to grow with each piece added, its edges expanding outward into new regions of uncertainty that had not previously been visible, revealing not a simple mechanism, but a layered and complex phenomenon that refuse to be reduced to any single, clean explanation. One of the most important developments in the study of this source came not from radio observations, but from a different part of the electromagnetic spectrum entirely. From the high energy domain of X-rays and gamma rays, where space telescopes operating above Earth's atmosphere could search for a mission that might accompany the radio bursts and provide additional clues about the physical processes at work. If the source of FRB 180916.J0158 plus 65 was indeed a magnetar, then one might reasonably expect to see X-ray emission associated with its activity. Because magnetars in our own galaxy are known to be powerful X-ray emitters, their intense magnetic fields driving currents through their crusts and magnetospheres that produce copious amounts of high-energy radiation. Several teams coordinated multi-wavelength observation campaigns, timing their X-ray and optical observations to coincide with the predicted active windows in the 16-day cycle, hoping to catch the source in the act of bursting and to detect any accompanying high-energy emission. The results of these campaigns were, in a word, sobering. Despite multiple careful searches with instruments including the XMM Newton Space Telescope, the Chandra X-ray Observatory, and the Integral Gamma Ray Satellite, no X-ray or gamma ray emission was detected from the direction of FRB 180916.J0158 plus 65 during any of its active windows. The source was, in those wavelengths, silent. Or at least, if it was emitting X-rays or gamma rays, it was doing so at levels far below the detection thresholds of even the most sensitive instruments currently available to us. This non-detection was itself informative, in the way that absences are always informative in science, not as proof that something did not exist, but as a constraint on how energetic or how luminous it could be. The upper limits placed on X-ray emission from FRB 180916.J0158 plus 65 by these non-detections were in some tension with the simplest magnetar models, which would have predicted X-ray luminosities somewhat higher than what the observations were able to rule out. This tension was not fatal to the magnetar hypothesis. There were plausible ways to reconcile the non-detections with a magnetar source, including the possibility that the magnetar was in a relatively quiescent state between major outbursts, or that the geometry of the system was such that the X-ray emission was not directed toward Earth, even when the radio bursts were. But it added another layer of complexity to an already complex picture, and reminded researchers that the observational constraints, taken together, did not yet point unambiguously toward any single model. Meanwhile, at radio wavelengths, new observations were revealing additional structure in the burst activity that had not been apparent from the initial CHIME data. Follow-up monitoring with the European VLBI network, the Effelsberg Radio Telescope in Germany, and other facilities showed that the active windows of FRB 180916.J0158 plus 65 were not uniform in their properties, Bursts detected during different active windows varied in their brightness, their duration, their spectral properties, and the precise timing of their arrival within the 4-day active window. Some active windows produced many bright bursts. Others produced only a handful of faint ones. Still others, according to the predictions of the 16-day ephemeris, should have been active, but produced no detectable bursts at all. This variability was important because it complicated the simplest versions of the periodic models. If the 16-day period were due purely to a geometric effect, if the active window simply reflected those days when the emission beam was pointed in our direction, then one might expect a more consistent level of activity during each active window, since the underlying burst rate of the source would not change from one cycle to the next. The observed variability in burst rate and burst properties from one cycle to another suggested that the intrinsic activity of the source itself was also varying, that the source was not a perfectly steady emitter that was simply being switched in and out of our line of sight by some external modulation, but rather something whose internal activity level fluctuated on timescales comparable to or shorter than the 16-day cycle.
This realization pushed theorists toward more sophisticated models, in which the period arose not from a single clean mechanism, but from the interplay of multiple factors. The orbital geometry of a binary system, perhaps, combined with variations in the intrinsic burst rate of the magnetar, driven by its own internal evolution, and further modulated by the changing properties of the material surrounding the source as the system evolved over time. Such models were harder to falsify and harder to distinguish from one another observationally, but they were also arguably more physically realistic, because real astrophysical systems are rarely as clean and as simple as our first theoretical approximations of them tend to be. And the history of astronomy is full of examples in which the initially simple model was gradually replaced by a richer and more nuanced understanding as observations accumulated and revealed the full complexity of what was being studied. One of the most striking observational results to emerge from the continued study of FRB 180916.J0158+65 came from an analysis of the frequency structure of the bursts, specifically from the observation that the bursts detected at different radio frequencies arrived at systematically different times within the active window, with bursts at higher frequencies arriving earlier in the window and bursts at lower frequencies arriving later. This phenomenon, known as frequency drift or subburst drift, had been observed in other repeating FRB sources as well. But in FRB 180916.J0158+65, it took on additional significance because of a separate observational campaign conducted simultaneously at multiple radio frequencies, which revealed a striking pattern. A team of European astronomers, publishing their results in a paper that generated considerable discussion within the field, reported that when they observed FRB 180916.J0158+65 at optical and ultraviolet wavelengths, far above the radio frequencies at which CHIME and other radio telescopes were observing, they found that the active window appeared to shift systematically
to earlier times compared to the window observed at radio frequencies. In other words, if radio bursts tended to arrive during a particular 4-day window within the 16-day cycle, emission at higher electromagnetic frequencies seemed to prefer an earlier phase of the same cycle, as though the higher frequency emission came from a slightly different region of the source, or was produced by a slightly different process, and as though the source itself had some kind of frequency-dependent structure that caused different types of emission to peak at different times. This chromatic behavior, the technical term for the frequency-dependent variation in burst timing, was one of the most theoretically rich observations yet made of this source, because it placed strong constraints on the possible physical mechanisms at work. In the orbital binary model, this kind of frequency dependence could be explained if the plasma surrounding the source, the disk or wind of the companion star, for example, had a frequency-dependent opacity, absorbing or scattering lower frequency radio waves more effectively than higher frequency ones. And if the geometry of the system changed as the source moved through its orbit in a way that caused the effective opacity to vary. During the early part of the active window, when the source was emerging from behind the densest part of the surrounding plasma, only the highest frequency emission could penetrate the absorbing screen. As the orbit progressed and the source moved to a less obscured position, progressively lower frequencies could also escape and reach our detectors. This would naturally produce the observed pattern of higher frequencies arriving earlier in the active window and lower frequencies arriving later, a behavior sometimes described as a cosmic sieve effect, in which the surrounding plasma filters the emission in a frequency-dependent way that encodes information about the geometry and composition of the binary system. In the precession model, the chromatic behavior required a somewhat different explanation, one in which the emission mechanism itself was frequency-dependent in a way that caused the beam at different frequencies to point in slightly different directions, so that as the neutron star precessed, different frequencies swept across the line of sight to Earth at different times. This kind of emission geometry was not entirely unprecedented. Radio pulsars are known to have frequency-dependent beam structures, with the emission at different frequencies coming from different heights in the pulsar magnetosphere, and thus subtending slightly different angles. But applying this concept to explain a 16-day period required additional assumptions about the neutron star's magnetic geometry that were difficult to independently verify. Neither model was clearly superior to the other in explaining the chromatic behavior, and both required some degree of fine-tuning to match the observations quantitatively, which left the theoretical situation in the productive but uncomfortable state of having multiple viable explanations and insufficient data to cleanly distinguish between them. What was becoming increasingly clear as observations of FRB 180916.J0158 plus 65 accumulated through 2020 and into 2021 was that this source was not merely an interesting curiosity, but a genuine laboratory. One of the very few places in the universe where the physics of fast radio burst production could be studied in detail over time, with the predictability of the 16-day period allowing astronomers to plan coordinated multi-wavelength campaigns in advance and to build up a picture of the source's behavior that no single observation could provide. The regularity that had initially seemed so mysterious was, in the deeper sense, a gift, a property of the source that transformed it from a fleeting phenomenon into something that could be studied with the kind of sustained, systematic attention that had proven so fruitful in other areas of astronomy. It was, in this respect, a window, not a complete or a perfectly transparent one, but a window nonetheless, into a class of phenomenon that had previously been visible only in fragmentary glimpses. And through that window, however imperfectly, the shape of something genuinely new about the universe was beginning to emerge. The galaxy that housed this remarkable source, the spiral galaxy at a redshift of approximately 0.034, catalogued in the NASA/IPAC extragalactic database as SDSSJ 015800.28 plus 654253.0 was itself the subject of increasing scrutiny as researchers sought to understand whether there was anything about its properties that might help explain why it hosted such an unusual FRB source. Unlike the dwarf galaxy that hosted FRB 121102A, which was a low metallicity, actively star-forming system of the kind thought to favor the formation of magnetars through the collapse of massive stars, the host galaxy of FRB 180916.J0158 plus 65 was a more ordinary spiral, with a star formation rate and the metallicity closer to that of our own Milky Way. The FRB source itself appeared to be located in one of the galaxy's spiral arms, not far from a region of ongoing star formation, a location consistent with the idea that it was associated with a relatively young, massive stellar remnant, as magnetars are expected to be, since they form from the core collapse supernovae of massive stars, and thus tend to be found near the star-forming regions where massive stars are born and die. This environmental context, the spiral arm, the nearby star formation, the relatively ordinary host galaxy, was consistent with, but did not uniquely confirm any particular model for the source. And it added yet another thread to the already rich tapestry of evidence and inference that surrounded FRB 180916.J0158 plus 65. The source was beginning to feel less like a single mysterious signal and more like a system, a complex, dynamic, evolving astrophysical object embedded in a real galactic environment, shaped by processes that extended from the quantum mechanics of neutron star interiors to the large-scale structure of the spiral galaxy that contained it, producing its remarkable 16-day rhythm through mechanisms that were slowly, carefully, and with great difficulty being teased apart by a community of scientists spread across multiple continents, using instruments of extraordinary sensitivity, thinking with extraordinary care, and listening, always with extraordinary patience, to what the universe was trying to tell them.
To appreciate the full depth of what the 16-day period represented as a scientific problem, it is necessary to step back from the specific details of FRB 180916.J0158 plus 65 for a moment, and consider the broader context of periodicity in astrophysics. To think carefully about what it means for something in the universe to keep time, and about what the existence of a precise, reproducible period tells us about the physical system that produces it. Periodicity in the natural world is always the signature of a cycle, of some physical quantity that increases, reaches a maximum, decreases, reaches a minimum, and then increases again, tracing the same path through its range of values over and over, with a consistency that reflects the stability and the regularity of the underlying physical process. In astronomy, the most familiar periodic phenomena are those governed by rotation and revolution. The spin of a planet, the orbit of a moon, the precession of a gyroscope, the pulsation of a variable star, expanding and contracting under the competing pressures of gravity and radiation.
In each case, the period is determined by the balance of forces acting on the system, and the stability of the period reflects the stability of that balance over time. What distinguished the period of FRB 180916.J0158 plus 65 from most other astrophysical periodicities was not just its value, 16 days, unusual but not impossible, but the nature of what was varying. In a typical variable star, what changes over the period is the star's brightness, its temperature, its radius, properties that vary smoothly and continuously, tracing a sinusoidal or nearly sinusoidal curve over the cycle. In a pulsar, what changes over the rotation period is the direction of a narrow radio beam, sweeping past the Earth like a lighthouse beam, producing sharp, brief pulses separated by long silences. But in FRB 180916.J0158 plus 65, what changed over the 16-day period was not a continuous physical quantity, but a binary state, active or inactive, bursting or silent, with transitions between these states that appeared to be relatively sharp, the source going from quiescent to active and back to quiescent over timescales of hours to days, rather than gradually varying over the full 16-day cycle. This on-off character was qualitatively different from the smooth periodicity of pulsating stars, or the simple geometric periodicity of pulsars, and it was one of the features of the signal that made it hardest to explain within any single, clean theoretical framework. The sharpness of the transition between active and inactive states, the fact that the bursts did not gradually become more frequent as the source approached the peak of its active window, and then gradually become less frequent as it receded, but instead appeared to turn on and off with a relative abruptness, was a clue that the modulation mechanism was not simply varying the efficiency of burst production continuously, but was instead switching between a state in which burst production was possible and a state in which it was not. In the orbital binary model, this kind of switching behavior could arise naturally if the modulation was due to absorption or scattering by a dense screen of plasma, such as the disk of a B-star companion, that the source passed through during a well-defined portion of its orbit. When the source was behind the screen, bursts would be absorbed and no signal would reach us. When it emerged from behind the screen, bursts would suddenly become detectable again. The transition would be as sharp as the edge of the plasma screen, which, depending on the structure of the B-star's disk, could be relatively well defined, producing the kind of abrupt switching behavior that the observations showed. This was appealing, but it required the geometry of the system to be just right. The inclination of the orbit, the thickness and extent of the disk, and the orientation of the system relative to our line of sight all had to conspire to produce a shadow of almost exactly 12 days, followed by a window of almost exactly 4 days. And while this was not impossible, it was not something that the model predicted naturally from first principles, without some degree of fine-tuning. In the precession model, the sharpness of the transition could be explained if the emission beam of the neutron star was narrow enough that it swept across the line of sight to Earth quickly, spending only a small fraction of the precession period aimed in our direction. A narrow beam would produce a short active window and a long inactive window, with relatively sharp transitions between them. The ratio of the active window to the total period, roughly 4 days out of 16, or about 25%, was a meaningful constraint on the beam width, and it implied a moderately narrow beam, not as pencil-thin as a pulsar beam, but not so wide as to be inconsistent with known neutron star emission geometries. What the precession model struggled to explain, however, was the observed duration of individual bursts, which, at milliseconds, implied an emission region of extraordinary compactness, alongside the precession period of 16 days, which implied a neutron star with internal properties that were somewhat difficult to reconcile with the same object producing such compact, energetic bursts. The physics of neutron star interiors is one of the most challenging and least well understood areas of astrophysics, involving densities and pressures that cannot be reproduced in any terrestrial laboratory, and that require theoretical frameworks, quantum chromodynamics, nuclear pasta phases, superfluid vortex dynamics, that remain subjects of active research and genuine uncertainty. In this context, the precession model could not be cleanly ruled out, but it could not be independently confirmed either, because the internal properties of the neutron star that would drive a 16-day precession were not directly observable. Alongside these two dominant theoretical frameworks, a number of more exotic proposals also circulated within the community, some of them representing genuine and carefully worked out alternatives to the binary and precession models. Others representing more speculative explorations of the theoretical space that were valuable less as definitive explanations than as demonstrations of the range of physical possibilities that the observation could, in principle, be consistent with. One such proposal involved the concept of a fast radio burst source embedded in an ultra-compact binary system, a system in which two neutron stars, or a neutron star and a white dwarf, orbited each other with a period of 16 days, with the radio emission modulated by the interaction between the two objects, rather than by the geometry of a wider binary with a normal stellar companion. Another proposal invoked the concept of a precessing accretion disk around a compact object, in which the disk precessed with a period of 16 days, and the precession modulated the flow of material onto the central object in a way that affected the burst production rate. Yet another explored the possibility that the 16-day period was not a true period at all in the dynamical sense, but rather the result of quasi-periodic behavior driven by some kind of instability in the source. A limit cycle in the mathematical sense, in which the system repeatedly approached and retreated from a critical state in a way that produced a characteristic timescale without any underlying simple periodic motion. Each of these proposals had its adherents and its critics, and the scientific literature of 2020 and 2021 accumulated a rich and sometimes contentious collection of theoretical papers, each making somewhat different predictions, each explaining some subset of the observations more naturally than the others, and none achieving the kind of clear consensus that would allow the field to declare the problem solved. This was not a failure of science, but rather science operating exactly as it should, in the messy, contested, productive way that it always operates when confronted with a genuinely new phenomenon. When the observations are not yet complete enough to uniquely determine the underlying physical model, and when the phenomenon itself is complex enough that multiple physical mechanisms could plausibly be responsible. The diversity of theoretical proposals was, in this respect, a sign of intellectual health rather than confusion. It reflected the genuine openness of the question and the genuine creativity of the community grappling with it. While the theorists debated, the observers continued to gather data, and as the body of observational evidence grew, certain patterns began to emerge that, while not yet sufficient to definitively identify the source, were beginning to narrow the space of viable models in important ways. One of the most constraining new results came from a detailed analysis of the polarization properties of the bursts, specifically from the measurement of the rotation measure of the radio emission, which is a quantity that reflects the strength and geometry of the magnetic field along the line of sight from the source to the detector. Radio waves traveling through a magnetized plasma undergo a process called Faraday rotation, in which the plane of polarization of the waves rotates by an amount proportional to the column density of electrons and the component of the magnetic field along the line of sight. The same line of sight magnetic field that, in the binary model, would be associated with the magnetosphere or wind of the companion star. Measurements of the rotation measure of FRB 180916.J0158+65 showed that it was relatively modest compared to some other repeating FRBs, notably FRB 121102A, which has an extraordinarily large and variable rotation measure, suggesting that it is embedded in an extreme magnetic environment, and that it did not vary significantly over the course of multiple active windows in the way that one might expect if the burst emission were passing through the varying magnetic environment of a B star's disk as the orbit progressed. This relatively stable and modest rotation measure
was more consistent with a source that was not deeply embedded in an extreme magnetic environment, not surrounded by the dense, magnetized disk of a massive companion star. And it provided at least some observational tension with the simplest versions of the BE/X-ray binary model. It was not, by itself, fatal to that model, because the geometry of the BE star's disk and its magnetic field could, in principle, be arranged in ways that produced a small net rotation measure, even if the total column of magnetized plasma was significant.